I'd like to thank Drew for a wonderful introduction. It's a tough act to follow Drew. He is top of his game there. I appreciate the way he set the stage for us all. I'd like to talk about three things today. Michigan's Coastline Viewer. I know most of you are familiar with that, but there's been some recent updates that I think are important for you to know. I want to talk about beach sediments moving offshore and the mechanisms responsible for that, and then wrap up with wind waves and water levels, which ties nicely into the background that Drew has provided for us, which was truly excellent. So on our Coastlines Through Time, this is the website. It's available to everyone. It looks at how our shorelines of Michigan have evolved essentially from 1938 to the present. 2020 is the last comprehensive photograph available. There are 6 time steps between 1938 and 2020 that we provide, and we have resolution of over 1,200 miles of Michigan's exposed shorelines down to the individual property owner level. So it shows how your property, your neighborhood, your community, your region has responded to these tremendous changes that we've seen in water levels, wave energy, and the other drivers of coastal change. We're, not perfect. There's some major exceptions to that coverage. Some of the 1938 original photographs have been lost over time. In the 2020, most recent ones are not over all of Michigan's shorelines. Tawas Point, and I know there's quite a contingent today from Tawas area. It's an area that I spent a lot of my summers in. There's some gaps that we're working very hard to fill, and this work has been supported by EAGLE, by the Coastal Zone Management Program. This is one of our poster child areas south of St. Joe Benton Harbor on Lake Michigan. This shows the long-term shoreline change. It's showing out here in the purple area that it's greater than 1 meter per year, so a little over 3 feet per year. The blue line out here is the 1938 shoreline. The orange line is the bluff line in 1938. This background is the 2020 image, so that's one of the updates. Here, the blue line is the shoreline in 2020 and the bluff line, and then the red hashed mark is if this erosion rate continues from 1938 to the present at the same rate, this is where the bluff line will be 30 years from the present. So that's kind of a scary prediction for a lot of Lake Michigan. We also have recalculated what we call the nearshore or the short-term erosion rate. Also, by checking a different box up here in the menu scene, you can bring this up. Typically, this is much greater than the long-term because this is 2009 through 2020, which is the rapid rise we just heard about in lake levels and the rapid change that has occurred along the coastline. The fact that it is very small in this example is because this coastline is almost 100% revetted. So the intersection of land and water is not moving in this short-term view as you would expect it to be, but that does not mean that erosion is not occurring. Erosion is occurring downward. The lake bed is deepening as a result of the revetment pinning the intersection of land and water. So just because we don't see it in a changed beach, it doesn't mean that erosion is not going on. And I'll come back to that point in a few minutes. So if we look at natural beach change and where this sediment is going, I want to talk about the natural beach and how it behaves, the effect of revetments, and the effect of groins and harbor structures. So a natural beach, the upper diagram is beach under low water levels. The wave energy at low water levels is less incident at the shoreline than it is during high water levels. The waves are more mellow. And the end result is a natural beach has the ability to store sand in this berm above water level. And the beach has the ability, again, if it's natural, to be able to reconfigure itself in the most efficient way, the most dissipative way to wave energy, as water level and wave energy changes. And it's constantly in motion in doing that. When we have high water level, the lower diagram, that beach then, in trying to flatten out its slope and create offshore bars, takes sediment away from this storage in the upland region, the berm, and transport that offshore into the form of our very common 3 sandbar configuration that we see along most of our sandy shores of the Great Lakes. And the purpose of those sandbars is to trip those larger waves that are occurring in high water times, to trip them offshore and breaking. They reform, break on the second bar, they reform, break on the most inward bar. So that is nature's way of dissipating that wave energy in a very efficient process. So if the beach is able to do that, that is what will happen over these periods of high water level. If you have a natural shoreline that is configured of rock, like we have a lot of in Lake Superior, or if it's artificially configured in rock, as with a revetment, that serves to remove sand from the nearshore region and store it in offshore bars. Essentially, the waves reflect off the hard barrier of the rock steep slope, compared to a natural beach, and pushes that sand further offshore. We began, after the high water in 1986, to conduct comprehensive surveys along Lake Michigan and Lake Huron shorelines. We continued that for some 20 years and then began starting that up again in 2020. So from 1988 to 2008, we had almost annual surveys at these locations all up and down the shoreline. This is an example of the area just south of New Buffalo, which has been pretty devastatingly hurt by erosion. And what I'd like to point out is, where is the sand going? So these are each survey that happened. The original ones in 1988 are the red lines, and you see an offshore bar, a middle bar, and nearshore bars. But what's really striking is here in 2020, during the high peak in water levels, is all those nearshore bars are totally obliterated. So this is the lime green line that I'm pointing to. And there's no inner bar, there's no middle bar. There is just one large offshore bar, and it's further offshore than we've ever seen before in the 34 years that we've been looking at this particular site. So the big events that were associated with high water and revetments have driven that sand further offshore, and we see a deepening in the offshore region that we had not seen before as well. Same thing happens with harbor structures or groins that were a common thing to do during the earlier high water levels in the Great Lakes. So whether it's a large harbor like St. Joe Benton Harbor on the left side, or New Buffalo on the right side, a recreational harbor, the same thing happens. Sediment is driven offshore by the jetties. You can see the sediment plumes out in this area, and you can see the same thing at New Buffalo here, driving sediment further offshore. Again, we're looking very conscientiously under NOAA funding to try and find out where that sand is being deposited, and whether it gets pushed offshore by these harbor structures or pushed offshore by hardened shoreline armoring. The question is, how far offshore can it be pushed and still return to the beach during low water levels? And we're seeing that there's a tremendous amount of sediment being pushed off into deeper water, and it's a loss of natural material from the nearshore region. Quick look at wind, waves, and water levels. As Drew perfectly outlined, we see major shifts in storm patterns on decadal types of scales. These are responsible for the precipitation and evaporation balance, as Drew pointed out, and ultimately resulting in high water level periods and low water level periods. But during those high water level periods, we are seeing more frequent and more intense storms. That's what brings the precipitation to the basins, but we're also seeing increases in wind and wave energy because the storms, again, are more frequent and more intense. And eventually that results into high water levels in the Great Lakes as the runoff component adds to what precipitation falls directly over the lake basins themselves. But it also causes increases in the wind strength, which is immediate with the arrival of the storms. And of course, the wind makes waves. So the wave energy is immediate with the storms. Wave heights and wave energy are on the order of 20 to 25% higher during high water years than they are during low water years. So when water level rises in the Great Lakes, we also have leading that a rise in wind strength and wave energy at the shoreline. So the shoreline takes a tremendous hit. This is a paper we published back in 1997. Over here on the left-hand side is 1958, and over on the right-hand side, 1992. So 32 years of water level data and wave energy calculated by the Army Corps of Engineers. So this is the wave energy and how it changed from 1958 towards high water level in 1986. This is a smooth line of the water level. And what we see is not only does wave energy rise as water levels rise, but the wave energy begins to come up about 18 months before water level responds. And most of that time is associated with the runoff working its way through the complicated mechanisms to get that back into the lake, get that water into the lake. But again, Corps of Engineers assessment of shoreline damages, two big peaks in shoreline damage, and they correspond with the peak in wave energy, not necessarily the peak in water level. So our takeaway from that is water level is the enabler. It changes the place along the beach or along property where waves can do their work, but it is the increase in wave energy that is really responsible for moving sediment out. Well, that was pretty exciting back in 1997, but does that happen again? So this is a new 42-year wave hindcalf that we did ourselves rather than relying on data from the Corps of Engineers that spans 1988 through 2020. So it includes the most recent high water level that peaked in 2019 in Lake Superior and then peaked in 2020 in Lakes Michigan and Huron. So again, the blue lines and the various graphs are all along the Michigan shoreline of Lake Michigan. These are locations where we also have coastal monitoring buoys. So the blue line is the rise in wave height, and the pink line, magenta line, is the rise in water level. So again, through 2010 on, this big shift that we saw in storm tracks and climate, we see in all these cases that wave energy along the Michigan shoreline, whether you're in the south part of the basin or the north part, begins to rise before the water levels begin to rise. So this has happened again in 2020. So we think we might be onto something there, that the wind and waves are a precursor to rising water level. Well, is that good news or bad news? And most recently, I'll draw you back to 2 weeks ago, a major storm in the Great Lakes. Wave heights reached 22 feet in Lake Superior and about 19 feet in Lake Michigan. So this is a major wind event that we saw in very, very recent history. 22-foot waves in Lake Superior are about a 50-year wave. That means we expect to see storms of that magnitude about once in 50 years. So is that signaling a new trend? So good news, Lake Michigan water levels, this is the most recent 6-month projection by the Army Corps of Engineers for October of this year. The next one will be out later this week for November. Recall Lake Michigan and Huron peaked in 2020. Been a nice decay in water levels here through 2021. And again, here through 2020, we still are seeing decreases. And then the Corps of Engineers projections here are showing a decrease on through the rest of the year for the next 6 months. Well, Lake Superior is not showing that. And again, recall when Michigan and Huron peaked in 20, Superior peaked in the year before, in 2019. 53% of the water of all the Great Lakes is in Lake Superior. Another way to say that is Lake Superior holds more water than the other 4 Great Lakes combined. So when Lake Superior starts to go up, it may be an indication, as Drew pointed out, that we're going to send you a lot of nice clean water from Lake Superior down to Lake Michigan and Huron. So I'm not going to go so far as to make a prediction, but as again was pointed out in Drew's talk, we expect to see more variability. There's no guarantee that we'll have 8 to 14 years of low water like we did leading up to the 2020 high water. It may not happen. So we are seeing greater variability in water levels. So I'll leave it at that and suggest that we might want to be watching for what happens in the very near future. Thank you very much.